Okay, so one of the things that we can do now is use the bisection and Newton's algorithms to find the implied volatility of an option. So basically, we can observe the option prices in the market, and given the market prices, the question is, what's the volatility, implied volatility, so that the Black-Scholes formula matches with the given market price. So this can be handled. Basically, we know the Black-Scholes formula now, and we have written the function for that. And basically, we have this right-hand side in this equation, which is the market price. So what we can do is we have the Black-Scholes formula minus the market price, and this will be equal to 0 in this representation. So actually, we are trying to find the root of the this term, which is the function with respect to the volatility of the option. So we are trying to find this right volatility that will equate the right-hand side here equals to 0. So how can we do that? Basically, in MATLAB, what you can do is first use your Black-Scholes pricing formula. Okay, so we have already introduced bisection algorithm before. So the algorithm part is already as same as before, as what we have discussed. So the difference is now I will give you a market price for the call option or for the put option, and then you will subtract this from your Black-Scholes pricing formula. So remember that in the bisection algorithm, we start with an interval, a to b, and then if there's a change in the sign of the function within from the left to the right hand side of this interval, if this change of sign occurs, that means there exists a root in this interval a to b. If there is no change of sign, basically, which is actually what we are checking in this highlighted area, in that case, basically, we tell the user that there is no root in this interval, so change the interval. Okay. So if the signs are different, then we will start our iterations. So the maximum number of iterations here is set as m, capital M, which is equals to 20 in this example. And remember that we are using our Black-Scholes formula to evaluate the function for any given volatility level C. Okay, so this C here is the midpoint that we are evaluating our function, and then if this W is already very close to 0 or equals to 0, that means we already found the root of this problem. Alternatively, if your interval size is already very small, at some point it will be already sufficiently small so that you don't need to continue to cut your interval into half. Okay, so we have the stopping criteria in these highlighted lines of code, and you can also notice that depending on whether the change of the sign is in the left half or in the right half, we can redefine these endpoints and continue to the next iteration until we achieve these stopping criteria, or we reach the maximum number of iterations, which is this capital M. At that point, we will get out of the for loop and return the result to the user. So let's apply this in this context. So suppose our initial interval a to b is from 0.05 to all the way 0.9. Since we are looking for the implied volatility, usually the range of reasonable values will be from some small number close to 0 all the way to maybe to 100%, which is equal to 1, right? So this is the volatility. So basically, we can run our code with this test example values and see whether we can get the correct answer. So you can see that if I run my code, here I see that the implied volatility that I get is around 25%. Okay, And how can I verify? Actually, in MATLAB, again, there's a built-in function to find the Black-Scholes implied volatility, and you can check your help file for this. So I just want to verify my result also by the built-in function, and I can say BLS implied volatility. So I'm going to use the same as 0. So let's put that as S. And then we have the K, which is our strike price. And then we have our risk-free rate, which is our, sorry, this is just R. And then we have the maturity time and this call price that I'm using as the market price in this example. So if I run this, so I can verify that basically both the MATLAB's built-in function and the bisection algorithm calculated the same implied volatility for this option.